Okay, we're not gonna do a quiz today, because I want to push in stuff you're gonna have to do with the assignment. Okay, so staying with familiar things, because we can, with the ramps and stuff, we can solve almost any problem. Any type of problem. So the problems that you get in the open math, my lab, are really the same problems we're talking about here. They're just in different situations, and they're more imaginative about their situations. I can get imaginative too, but you really don't want me to. But if we confine ourselves to things we can really see here in the lab, it makes more sense, and things you've had your hands on. Okay, so 2 ramps. $60 centimeters each. Okay. One ball rolls down in 5 seconds. In 5 seconds. The other rolls down in 4 seconds. They each roll down a different ramp. Okay. So the question is, how far ahead is the second ball when it reaches the end of this ramp? Can't we assume the ramps are parallel? You understand what I'm talking about, because we looked at the ramps and so on, distances and estimated and so forth. Okay. Okay, so for the first round. What do we know? Well, we know the displacement, x minus x naught. We know the time. Yeah, 5 seconds that first round. We know the uniform acceleration. We know the initial velocity. Yeah, how fast is that thing going when it starts? It's not moving. Okay. No, I didn't say rolls down in 5 seconds. So let's just clarify that. And it's implicit because we've looked at the situation and that's what we did. But let's be explicit, it rolls down from rest. Since it rolls from rest, V naught x equals 0. Now, how many of these quantities is that? Show me with your fingers. Yeah. Okay. It's 3 quantities. So if we're going to use the equation, and there's actually an easier way to do this than the equations, it's more intuitive. It's what I'm actually going to do. Okay. But we've now find an equation that has all 3 of these. Okay. Now, does equation 1 contain all 3 of these? X minus x naught t and v naught x. Well, right there's x minus x naught, right? There's t, there's v naught x. What don't we know? We don't know the acceleration. So we could use the first equation to very easily find the acceleration. Okay. Now, is there another equation that has those quantities? Well, this one has a Vx, and I said Vfx. I often use Vf, but I think your book actually tends to want to use just Vx. Means the same thing. Means velocity after time t. Okay. There's velocity at time t. So we don't know Vx. We don't know how fast this thing's going at the end, but we're going to find it pretty quickly. We do know V naught x and we know t. We don't know ax either. So this equation is not going to do us any good unless we find either Vx or ax. Okay. So we can't use it right away. But if we were to solve this one for ax, then we'd have ax and we'd be able to find Vx. It's just a matter of bookkeeping. How many other variables that we know will fit, or how many equations are there that the three variables that we know will fit? Okay, this one, we don't know Vx, we don't know ax. What about this? Well, we know x minus x naught, we know V naught x, and we know t. So we could use this equation to find Vx. So, or we could use this equation to find ax. Okay. So I'm just going to say the first equation will give us ax. The fourth equation will give us Vx. Right? So we plug these numbers in. Well, first of all, we solve this equation for ax. Okay. So solving this equation for ax, well, how do we solve it? Well, we subtract V naught t from both sides. Okay. Then we multiply by 2 over t squared. So I assume everybody can easily enough solve this equation for ax. So when we subtract V naught xt from both sides, we get this. Now that doesn't quite give us ax, that gives us 1/2 axt squared. And if we multiply by 2, then we get rid of that 1/2, but then we got to divide by t squared, right? In this case, it's really simple to find ax, and we don't have to do that, okay? But that we could do that. We could solve this equation for ax. It's more involved than it really needs to be, as you'll see in a minute. We solve the second one for Vx, okay? Well, what do we have to do here? First of all, we can multiply the x minus x naught by 2 over t, okay? So we get Vx equals 2 over t times part of the x minus x naught. But then we still have a V naught x over here that we have to subtract from both sides. Well, there it is. Okay. Now that's a perfectly good strategy for solution. Now, which equation would you rather plug your numbers into, this one or this one? This one, you don't have to square t and stuff like that. It's all linear, okay? I mean, it's not a linear equation, but the numerators and denominators are all linear, so makes it easy. Okay, makes it even easier because V naught x is 0. So V naught x being 0, forget about it. We know x minus x naught. Okay, it's 60 centimeters. We know t, it's 5 seconds. So we have 2 times 60 centimeters divided by 5 seconds. Now, if you write that out, it becomes really clear. But that's algebra that everybody knows how to do. So this is 120 centimeters over 5 seconds. Okay, which is 24 centimeters per second. Now, if you're comfortable with just using the basic relationships, that average velocity is change in position divided by time, and that acceleration, if it's uniform, is equal to the change in velocity divided by time. Okay, you do this. Okay, you say, okay, well, I know what the average velocity is. Okay, that's like distance equals rate divided by time, but you got to identify the rate. It's the rate of change of position with respect to time. So that rate is your average velocity. Now, just intuitively, if you travel 300 miles in 6 hours, you can immediately say, okay, that's going to be 50 miles per hour, right? You just divide how far you go by your time. And that's all we have to do here. We divide how far we go by the time, and we get 12 centimeters per second. 5 goes into 6 to 12 times centimeters divided by seconds is centimeters per second. That's our average velocity. That's not helpful unless we know the initial velocity. It's especially helpful if the initial velocity happens to be 0. Then the average velocity being the average of initial and final velocity. If the initial velocity is 0, the average velocity is just the final velocity divided by 2. So the final velocity is 2 times the average velocity. Okay. So when you're starting something from rest and you know how long it goes and how far it goes, you say, okay, the average velocity is, in this case, 12 centimeters per second. Initial velocity was 0, so the final velocity is double that. So the initial velocity isn't 0, you better not do that. You better understand why you're doing it and how that applies the definitions of velocity and acceleration. Okay. So we get that 24 centimeters per second without having to go into these equations. There are plenty of times you can shortcut, but for right now, be sure you do the equations and then do whatever shortcut you thought was going to work. Builds insight. So that shortcut gives us the same result the equation did. Then, I wouldn't use this equation, but maybe I would. There's a good argument for it and a good argument against it. Maybe I do both. I can take that 24 centimeters per second, and what am I still trying to find? I'm trying to find Vx. No, I just found Vx. I'm still trying to find the acceleration. Okay. I could use this equation, which is these two equations are really simple because they're nice and linear. If you can use them, good idea to use them. So we can solve for AX. We solve this one for AX, it's just Vx minus V naught over T. Change in velocity divided by time. We don't even need an equation to know that. What's the change in velocity? 24 centimeters per second. What's the time? 5 seconds. What do you get when you divide 24 centimeters per second by 5 seconds? You get 4.8 centimeters per second squared. I think we did this in class last time, but less formally, less meticulously. Okay. Well, this will give us 4.8 centimeters per second squared. if my reasoning and my arithmetic were correct, and that's always something you want to check. So you plug all the stuff into this equation, and if it doesn't come out this way, it means either I made a mistake, which is inconceivable, or there's something wrong with the equation. Okay. Well, if it doesn't come out this, I made a mistake. Okay. Don't think I did in this case because it's pretty simple. But never know. Usually. Okay. Now, quickly solve it for 4 seconds. Right now, we've got all we need to write out the displacement, the equation for displacement as a function of time, or any of these other equations. Okay. So if I'm wanting to ask you, for example, well, actually, I've solved the whole thing. I know everything there is to know. Okay. But I still have an equation that we might want to use. Okay. I know that for whatever time now, if I leave time unknown and plug in numbers I got, 24 centimeters per second there, 4.8 centimeters per second squared here, and x naught equals 0, then I know my function x versus t, and I know it has a parabolic graph because this is a quadratic function of time. And then I can use that parabolic graph to help me reason things out. And we talked about that toward the end last time. Okay, well, if we solve the second equation, and I'll just write it down here, I'll just write out the solution because using the shortcuts, I know that it's going to go 15 centimeters per second on the average, so it ends up at 30. So the acceleration is 7.5 centimeters per second squared. Okay. You know what? I got a bad habit of believing what I see. I'm seeing that 5 seconds up there. Oh, that wasn't the first round. Never mind. Thought I made a mistake, but didn't. Okay. Happens every time I think I make a mistake. I never do. Okay. So we get this same process. You can do it mechanically once you identify the 3 quantities. Of course, the 3 quantities in this case would be 60 centimeters, 4 seconds from 0. Okay. Then we plug into the same equation if you use the equations. And you should use the equations so you get ready, used to using the equations. Okay. Once more, once we solve for Vx here, we can plug into this equation. The advantage to using this one instead of or in addition is this equation uses only the information you identified. It doesn't use information you calculated. So if you made a mistake in this calculation and use this equation, you'd have a mistake for Vx. Or for AX. Okay. Whereas if you use this equation, you might have a mistake over here, but you don't have one here. So 2 ways to do this. It's quicker and easier to just plug this in here. But you really want to check it out. One of the other equations, if it's really important to get the right answer. If you're an engineer, it sure is. Okay. And if you're a physician's assistant, you want to know what it means to do the right thing. Okay. And learning to do the right thing in this context transfers over if you really learn. Okay, which is why I want you to have a physics course. Okay. So there's the scheme. There are some of the details. You need to fill in the rest if you do it originally, okay? That's how we solve these problems. Okay. Now I can ask additional questions about this situation because, you know, what I really asked was how far ahead of the second ball is the first one when it reaches the end of the ramp, right? So now we can take our information and do what I said. About this, okay? And X naught is implicitly zero. So X naught is zero. So we've got an equation for X of T. If you want to do the thing engineers always do and not write units, do this. Specify that X has to be in centimeters and T has to be in seconds. If I talked about the Mars probe back in the 90s, what the engineers did to it, they crashed it into Mars because they didn't use units. There was a quantity that they just wrote as a number. It's supposed to be in kilograms and they use pounds. So when they did the last burn, they just boom. Okay. Yeah, several $1 billion because somebody didn't use units. Okay. You don't want to be that engineer. Okay. Be very careful with your units. I'm not real tolerant. I penalize unit errors more heavily than I do just simple arithmetic errors. Okay. I'm not absolutely strict. I'm not going to give you 0 on a long problem because you messed up the units. But if your answer makes absolutely 0 sense and you don't notice that the answer made 0 sense, you're probably going to get half credit even if you did everything else right. Okay. And that's important for everybody. You got to know how to be right. As an engineer, you got to know how to be right. As a medical practitioner, you got to not kill people. Okay. 2 basic principles. Don't waste billions of dollars. Don't kill people. Okay. So we have now a function. Now, since it's first ball, we're going to put subscripts on these. Got X1 and T1. Okay. Then it's 3.375. Leaving the units off if we do this. And if I see somewhere in your work that you have actually checked out the units, which basically means you wrote these things in units and then you use the units when you plugged in here. We don't just plug in numbers at this last step. We plug in numbers with units. And we do the algebra to show if the units really come out. It's another way of avoiding errors, which is critical to everybody's future success. Okay. Okay. So we have these, and we also have yeah. So our position and our velocity and our acceleration, we know it all. Okay. Here I suppress the units, although it's not a bad idea to write 4.8 centimeters per second squared and 7.5 centimeters per second squared. Not a bad idea anywhere. Down here, I go ahead and write the units. I could write to the side A1 and A2 in centimeters per second squared, but it's easier just to write it out. You remind yourself what the units are and remind yourself to think about the units. Okay. Now, use the information that we got, the equations that we have up here, and see if you can answer the questions. We want to focus, because what we want to do is we want to find out how far ahead the second ball is when it reaches the end of its ramp. And I'm going to say, that means you can find X1, X2, B1, B2, and T. Once you find all those things, it's real easy to answer that question if you know what everything means. And I think you do. So of all these quantities, which one is the easiest to find? Actually, pretty much need to find just one of the quantities. You need to kind of focus on that. If you focus on the event that defines everything, that's the event of the ball reaching the end of the ramp. Then you get all your positions and all your velocities and the time. Okay, along the lines of eliminating anything ridiculous. Okay. 24 T1 can be 24 centimeters per second times T1. It's supposed to be initial velocity, right? So I was trying to emphasize the units, but you don't have that. And you don't have this. That's a zero. You just have like this. And similarly down here, initial velocity is 0. And if you plug the numbers in to what I wrote down there, you'll immediately get a ridiculous result. Okay, you'll find that the ball went through the wall and into the hall. Okay. So you want to be attuned to ridiculous results. Didn't need to introduce the idea right now, but there it is. Okay. Yeah, I simply wrote down the final velocity carelessly. Or would I use the initial velocity? Okay, so okay, at this event, T is 4 seconds because the event is first ball reaches the end of its ramp, right? Second ball reaches the end of its ramp, which happened in 4 seconds. Okay. So if you were looking into the equation formulas for that, look a little further back. Look at all your information, and it's right there. And of course, if you're really visualizing the situation or you have it in front of you in a lab situation, then you really do know it in a tangible way. So anyhow, if T equals 4 seconds, now we get all these just by plugging in 4 seconds, right? So I'm going to use the units. For 4 seconds, we get 16 seconds squared. And 16 times 2.4. Okay, that works. It's 38 point. .4 centimeters, right? Okay. At this point, we can answer the original question, can't we? Okay. So how far ahead is the second ball? Well, it's going to be 60 centimeters minus 38.4 centimeters. Okay. 41.6 centimeters ahead. Now, we can plug in for X2. If we plug in for X2, plug in 4 seconds, we'd better get 60 centimeters because X2 is the position after 4 seconds, right? Well, we square 4 seconds, we get 16 seconds squared. 15 fourths times 16, 4 goes into 16, 4 times 15, 16. And the units work out the same as the units here. Now, I could have asked, how much faster is the second ball moving? Okay. So let's go ahead and ask that question. I don't know, keep this here. I don't want to write out. The person reaches the end of its ramp, the event is shorter, you know what the event is, okay? Well. V1 of 4 seconds is 4.8. Centimeters per second squared times 4 seconds. And that equals 19.2. That does come out in centimeters per second because second in the numerator, second squared in the denominator gives us a second in the denominator. So our spacecraft is still on track. It's not likely to, this won't be our fault if it crashes on Mars, okay? Okay, so. And V2 of 4 seconds equals, well, we know it equals 60 centimeters. But we probably want to plug the 4 seconds in anyway. 4 seconds times 7.5 centimeters per second squared. 4 times 7.5 is 30. 60. T. Check my units. Oh, okay. That's acceleration. This is time. It doesn't give us displacement. Okay. Okay. So how much faster? Well, you subtract this from this. You can answer all these questions. You can tell me anything that's going on at that event. As far as the position and velocity of the two balls. Okay. Now, how about this? Put the speed of the second ball and the first ball is halfway. Or to release the first ball so they reach the end at the same time. Assuming we release the two balls at the same instant. So assume a simultaneous release. release on the top of each ramp. How much do we want to delay releasing the first ball? Wait a minute, first ball. Sorry, the second ball. No, the first ball got to be released. No, which one's going faster? Second ball going faster, so it'll be the second ball. Sorry. Okay. So where we'll release it. And overlook this, so it shows on the video. These two portions did. No, I think this one does. Got used for some. Okay. So how do we set these situations up? I think two of them can be answered using the solution we already have. And I think there might be at least one, maybe two of the others that have to be set up slightly differently. So we want to talk about how we would modify our setup. It can be helpful to have a graph that shows X versus T for each ball. Okay. At T equals 4 seconds, the second ball has gone a little more than half as far as the first one, right? So I would put 4 seconds. So if I put 4 seconds here, second ball will be twice as far, more than twice as far as, sorry, the first, this is the second ball. This is the first, okay, sorry. Okay. If I put like 4 seconds here, if I look here, the second ball will be more than twice as far as the first. If I put 4 seconds over here, the second ball is still more than twice the distance of the first. So it's not a particularly good diagram, but let's just say, okay, here's 4 seconds. And this would be 38.4. Put the units on the axis, so I don't have to run them. And this would be 60. Not a particularly realistic picture. The graph of the first ball should be a little steeper, but you get the idea, right? You want to start thinking in terms of these graphs, because the graphs can really help with some of these questions. Especially the one about the time delay.